Hi, everyone. Thanks for joining this session. My name is Varun Tyagi, and I'm here with my teammate Daili Zhang. We're data scientists at Halliburton, which is an oil and gas services company located in Houston, Texas. And today we're going to talk about how we use Databricks efficiently to help build machine learning models for predictive maintenance. And before we get into the topic, we'd like to introduce our team first. So we're part of a department called Halliburton Digital Solutions, and the main function of HDS is to support and consolidate digital transformation across all product service lines, which we call PSLs. And so at Halliburton, we have about 14 PSLs, varying from drilling to cementing to health and safety and to completions. And our digital solutions group provides common platforms and architectures for data warehousing and governance, to analytics development, to business intelligence reporting. And we streamline and consolidate various processes across all the product service lines. And we also provide and build a strong talent pipeline for software and digital development within each product, within each PSL. Daily and I, we're in the data science team within HDS. So our roles are to develop analytics and machine learning models to improve operational efficiency, increase productive uptime, and reduce operational costs, and provide insights at the right time to the right people to help them make business level decisions. So at Halliburton, we follow the basic analytics development lifecycle with some variations specific to our use cases. So we have thousands of rigs all over the world, and each rig contains lots of tools equipped with various sensors that are collecting information in real time. And we also have large amounts of data stored in SAP and other SQL databases as well. And over the years, we've collected petabytes of data in different file formats like PDFs, CSVs, and Parquet formats as well. For each project, we first identify the different data sources and then collect and integrate the data into the same platform. And once we have ingested the data, we spend the majority of our time cleaning, aggregating, and transforming the data. We then perform, feature engineering with the help from domain experts, and then we train and test our models, and we select models based on different metrics. But most of the time, the metrics are chosen such that they're directly related to the economic impact. And we then deploy the models and show the results to related personnel. And after the models are deployed, we monitor their performance to check for any drifting, and then we diagnose and retrain the models if needed. And no doubt, the model training and testing is an essential part of the cycle, but in reality, it takes less than 5% of our time. And so we spend the majority of our time with the data ingestion and cleaning process. So what kinds of data do we have? We have three main types of data. First is operational data, which includes historical data and real-time data from edge devices. And most of the historical data is stored in what are known as ADI files. And ADI is just a proprietary format to Halliburton. And for one of our product service lines, we have more than 500,000 ADI files, and each file is about 3 gigabytes in Parquet format. So in total, we're dealing with about 1,500 terabytes of data. And we're getting more and more real-time data from edge devices in recent years. And so this volume is growing fast. The second type of data is hardware configuration data, maintenance data, and some other event-related data that comes from the field. And those types of data are normally stored in SQL databases. And so, for example, we have collected over 5 million maintenance records in less than 2.5 years. We also use external data when it's available. For example, we use weather data, geological and geophysical data when needed. Um, so in summary, we don't lack data, and we're getting more data on a daily basis, but we do sometimes lack data with good quality, and particularly historic data. But with the edge devices and a more rigorous data collection process, we're starting to get better, good quality data. So here's an example of a use case for predictive maintenance. The objective of this particular project was to reduce annual maintenance cost by 10% through field operation optimization based on avoiding failure modes for transmission assemblies. So the picture shown here is one of our fracking trucks in the field, and the transmission of the truck is located in the middle, and it connects the engine to a high pressure pump. And the role of the transmission is to transfer energy from the engine and drive the high pressure pump, which pumps the liquids into the drilling well. And it's a very expensive piece of equipment. So for this project, we have to combine or marry the operational data and the configuration and maintenance data in a consistent way. In this process, we face a lot of challenges. The operational data that we collect it sometimes comes in different sample of frequencies, varying from 1 hertz to 1,000 hertz. So we either have to downsample or oversample different data sets and conduct synchronizations between the various sensor data and also between non-sensor data like maintenance records. For our maintenance related data, we have a lot of free text inputs. So we have to use natural language processing techniques to extract the information that we need. There's also a lot of manual effort in coming up with programming logic to pin down which records belong to which equipment IDs, since the records come from various sources and each source may not have a consistently formatted equipment identifier. And by the nature of the equipment being used, they're quite frequently moved from site to site and job to job. And each job may last for a couple or more days. But within each job, the equipment is constantly starting up and shutting down. So we need to account for the transient and steady state modes of the equipment as well. So we faced a lot of missing data and a lot of erroneous data from faulty sensors or bad user inputs quite frequently. Thankfully, we have Databricks, which helps us process the huge amounts of data sets quickly and in a scalable way. And currently, we're running on Databricks Premium Workspace, and everything is transparent to the rest of our team members. We share and collaborate with different notebooks, different utility functions, and go back and forth with different versions of notebooks through version control as well. We also leverage the advantages of Delta Lake to speed up querying and going back to certain time snapshots in the data as well. We also leverage Panda's user-defined functions quite a lot. And Panda's UDFs, they're executed by Apache Arrow to exchange data directly between the JVM and the Python driver and executors. And it comes with near zero serialization or deserialization cost. And its vectorized operations have helped us gain about 100 times speed improvement over ordinary PySpark user-defined functions for certain calculations. And we'll show a simple example during the demo on one of our use cases for Panda's UDF functions, where we fill in the null values in a data frame with either the previous valid value or the next valid value. For this case, a PySpark user-defined function took about 4 to 5 hours, but with a Pandas UDF, it took about 6 to 7 minutes, and this was a huge improvement for us. And no one wants to wait for 4 to 5 hours for a piece of code to run. Just waste time and computational resources. For this project, we did a lot of feature engineering. We combined different features using different formulas based on domain expertise. Um, so here, for our projects, we're dealing mostly with time series data. So we use a lot of techniques from signal processing. The example shown above, we use windowed Fourier transforms to obtain frequency domain features for different time windows. And as I mentioned before, the equipment that we study, they're moved from job to job and site to site. And so they constantly turn on and off and load up at different at different rates and shut down. So the first thing we did is to select sets of high load windows based on a threshold. So for example, we could use like a certain threshold for engine RPM, and above that threshold, we would consider that a high load. So we select windows of data based on those thresholds that contain continuous data. In our original time series Spark data frame, each row corresponds to one time point, and each column is a feature. So we're able to use the collect list function to collect all the time values and the corresponding data within each time window into an ordered array. And after this operation, the data for each time window gets collected and transformed to a single row in the Spark data frame. Then we're able to perform the Welch Fourier transform on that data for each window and transform it into the frequency domain. Then we can select the peak values from the frequency decompositions for each window and then use those as features into the machine learning models. And frequency domain features like this helped us improve our model accuracies. So I will now hand it over to Daili to describe the machine learning process.
Thanks, Maria. So after we finish all of the hard work, like data cleaning and data aggregation and feature engineering, and we trained and tested the model with various methods. We tried like Spark ML, and we tried deep learning. We tried Azure AutoML and XGBoost and sklearn, etc. And we evaluated the models with various metrics, such as like recall rate and F1 score and accuracy. And so in the end, normally we pick the model based on its economic impact. So the table on the right shows like some comparisons among different ML packages and we explored. So as you can see from the table, so the deep learning, which use LSTM on a GPU virtual machine, it took days to finish one training. And Azure AutoML is relatively fast, so and provide a slightly better results for this specific use case. So in the end, and for this project, we realize so basically different models does not make any significant differences, but the different features and getting into the models have far more impact. So for this project, and we use the Power BI to visualize the results and show that to the end users. So we modularized the whole process from extracting the data and performing the data cleaning and data aggregation and creating features and calling the model to perform predictions and then writing the results and back to blob storage into different notebooks. So the notebooks are orchestrated to run through Databricks notebook workflows. And based on the business requirement, and we normally schedule the job to run every 24 hours. So we'll show a demo in the end about how we utilize the notebook workflows to run the notebooks. After we deploy the model, and we do monitor the model performance over time to check if there is any model performance drifting. So what we did is we store the predictions into blob storage continuously. And we also store the actual results from the field into the blob storage continuously as well. So we show the discrepancy between the predictions and the actual results along the time in Power BI. So some alerts are set to send emails or text messages to our team based on some preset thresholds. So, and once our team receives the alerts, and we will investigate the model drifting and may retrain or like redeploy the models. So model management is a big part of the whole process, especially when we're getting more and more models. So prior to using MLflow, we manually wrote the model specific information into a CSV files and store the models and its corresponding environment running information into a blob storage with certain name conventions. That actually takes a lot of time and also cause some confusions and inconsistencies over time, especially if we are getting more and more models. So MLflow and offered by Databricks, it greatly simplifies the process with consistency and quality control. So in the end, we will show a demo about how we utilize MLflow to manage the models. So that's it. So and we'll show the demo. For the demo, I want to share 3 items, which either improve the performance and run the code faster or speed up the development process. So before I show the detailed code, I want to show the configuration of the cluster first. So the cluster is called signal process. So if you go to the configuration page, it has up to 12 worker nodes. And each worker node is with 64 GB memory and 16 cores. And the driver node is 256 GB memory and with 64 cores. So it's a big cluster because we have a big data set. So now let's go to the first item where we utilize pandas UDF function to do one of the cleaning process. It's called the fill-in data notebook. So in the notebook, the first thing we do, we read in the data from the blob storage into the data frame, into a Spark data frame. So after we read in the data, we do some pre-process. And here I output the size of the data frame. As you can see, the data frame has 168.2 million rows and 74 columns. So it's a big data set. So here we're trying to do is we want to fill in the missing data for each column by using either the previous available value or the next available value. So we use pandas UDF function to achieve this goal. So here's the definition of the pandas UDF function. So the first thing you do, you declare the pandas underscore UDF decorator. So what the decorator does is to do some pre-process and post-process of the data into the panda function. So here is the main body of the panda function. So as you can see, it's very simple and it's pure pandas syntax because it's a panda function. So after the function is defined, and we call the group by, and then we call the apply. So basically what it does, it splits the data into different groups based on the pump ID, and then it applies the pandas UDF function we just defined on each group independently. And in the end, it combines the results back into a data frame. So after that, we write the data out to the blob storage with Delta format. So as you can see here, the whole process took about 7 minutes to run. So if you want to achieve the same goal by using Spark or Windows function to fill in the log values for each column based on the pump ID, it will take about 7 hours. So the speed is almost like 16 times, right? Times faster. So I would highly recommend you to check the pandas UDF function out. And trust me, and you will love it. So the second item I want to show is notebook workflows. And let's go to the notebook. We are using the notebook workflow flows to run all of notebooks. So it's in the signal process. It's automate ML flow on notebook. So notebook workflow lets you run a notebook from another notebook in a defined way. So it's a complement to %run command. The advantage of notebook workflow, it can pass a set of parameters to the target notebook defined in widgets, and also it can return a value, which you can use that to condition other notebook runs. As we mentioned in the presentation, we modularize each step of the whole ETL process and modeling process into different notebooks. And then we synchronize all of the notebooks to run in one notebook. So it's a more organized way, and it's easier to debug and manage for the whole process. So the syntax of the notebook workflow is very simple. So it's called dbutils and .notebook.run. So the first parameter is the path to the notebook you're trying to run. So the second parameter is timeout in seconds. So this parameter is to control the timeout of the notebook run, so target notebook run. So basically, you don't want to waste the resource to run a notebook for a very long time due to some code issues, which is a waste of money, right? So the last parameter is a dictionary. So it basically passes the parameters into the widgets defined in the target notebook. And it can, here I didn't return a value because we don't use the return value for anything. So let's go to the target notebook to see how the widgets are defined and located. So that's the first one. It's select the condition data. So as you can see, in this notebook, we defined 3 widgets. So actually, the Databricks provides all kinds of widgets you can utilize. So and it's well documented on the website as well. So if you want to know how to define widgets, and just check the documentation out. So the last item I want to show is ML flow. So ML flow is used to manage the whole modeling process and also the models. So we currently we only use ML flow to do the model tracking and also call back the models to do the predictions. So ML flow has more functionalities and it's growing as well. So it can like register the models and call the models through the API, through the REST API, and also it can use it to deploy the model into containers as well. So here we will only use the ML flow to tracking the models. So of course, in order to use ML flow, you need to install the package as you normally do to use some other packages, right? So the first thing we do, we create an experiment. So here we specify the experiment path and the name. So it's in the workspace. And then we basically create the experiment. After this, command cell is run, and the experiment will show in the workspace. It's here, it's transmission underscore exp underscore 01, right? So after the experiment is created, and we can log the runs into the experiment. So here is the syntax to log the parameters and the runs into the specified experiment. So in this application, we log all of the ETL parameters And also we log the hyperparameters from the XGBoost modeling part. So, and for this application, I log the model, of course, and also I log the confusion matrix and the features used to run this model, and also the features importance bar chart. So after that, and all of the runs are logged into the experiment. So let's go to the experiment to see what we have logged. So double click that, and it will get into the main page of the experiment. So as you can see, it logs the date and the run name and who runs that and what resource and all of the parameters and matrix. So let's double click get one of them and get into the details. So here, as you can see, it's logged all of the parameters and the matrix. And I want to show like all of the artifacts we have logged. So the first thing is called XGB cluster. So it's the model part, right? If you it has 3 atoms, the ML model. So it basically specifies all of the modeling information, and it has the environment file, and it specifies all of the package dependencies we've used to run the model. And of course, the model itself is in picker format. And we log the pre-process as a model as well, so it's similar. And we also log the confusion matrix as a picture. So you can download the picture or copy paste the picture into your report. It's very convenient. And we log the importance, the feature importance bar chart as well. So, and also we log the feature, all of the features into a JSON file. So this will help us to reproduce the model because we know what features have been used. It's very convenient. So that's it. That's what I want to share today. And thanks for everyone to listen what we did.